Hello, my name is Isabella, and I will be your host for another mathematics video brought to you by RJ. In a previous video, I asked, when is an image an integer? In that video, we answered that question by deriving the integer test function. If you haven't seen that video, I suggest watching it now. The next natural question to ask is, how many integers are there within a certain interval? In the previous video, we used the identity function as an example. So let's use it as an example again. Here we have the graph of the integer function of the identity function. We will call the left interval A. We will call the right interval B. I have randomly chosen intervals A and B. A and B could honestly be any numbers. So in general, if both A and B are integers, then there are B minus A plus 1 integers between A and B. If A is an integer but B is not, then there are the floor of B minus A plus 1 integers between A and B. If B is an integer but A is not, then there are B minus the floor of A integers between A and B. If neither A nor B is an integer, then there are the floor of B minus the floor of A integers between A and B. For these formulas, we are assuming A and B are included, meaning they are closed intervals. Of course, these formulas are true only when working with the identity function. This is because, as I said before, each integer occurs every 1 unit. This may not always be true for images of other, more complicated functions. I'll leave it to you to check that. We want a way to determine how many integers there are within a certain interval for any function. The images for the integer test function are either 0 or 1. We know 0 has no effect under addition, and the integer test function produces a 1 only when a function's image is an integer. So we can just add up all the images between intervals A and B. We now have a formula which is a discrete summation for determining how many integers there are within a certain interval. This is suitably called the integer counting function. However, we may need to modify the starting point depending on whether or not we want the floor of A included. If we don't, add 1 to it. For the rest of this video, let's assume we do want to include it. This is a great solution for what we are looking for, but can we transform this so that it spans a continuous domain, just like the integer test function? The continuous version of a discrete summation is the integral, which is the sum of a bunch of areas under a function. Remember, an area has both width and height. Let's look at the graph again. Each of these points has a height from the horizontal axis, which is 1, but points do not have width. Therefore, they have no area. Since they have no area, the sum of their areas is 0. This may sound discouraging, but can we get around this issue? Yes. We can transform the points into horizontal line segments, which do have width. We can do this by placing our pre-images inside the floor function. By doing so, every non-integer pre-image has the same image as the integer image before it. As a result, each line segment has a width of 1 unit. Since each line segment has a width of 1 and its height from the horizontal axis could either be 0 or 1, the area under each line segment is either 0 or 1, which is equivalent to each point having an image of either 0 or 1 in our original discrete summation. Thus, We now have a formula for the integer counting function that spans a continuous domain. This +1 is due to expanding points to the right to transform them into line segments. We have two equivalent formulas for how many integers there are within a certain interval. One discrete, one continuous. Even though they do the trick, as we can see, neither of them look very pretty. The question now is, can we do anything more with them? Is there a closed formula for either of these? Stay tuned for a future video. I hope you enjoyed the video. Thank you for watching.